All right, so we have the last of the tests for convergence tonight. So there's really two tests, the ratio and the root test, which we're going to talk about in a little bit. But before we get to those, we want to talk about something what's known as absolute convergence. So a series is absolutely convergent if its absolute values are convergent. So what that basically means is that if I can take the absolute value of all the things or all the series, and that series that is convergent, then the positive version is convergent and the negative version is convergent, and the alternating version is convergent. So every possible combination of these is going to be convergent, and that's what's known as absolutely convergent. The ratio and the root test basically dictate those. So when we use the ratio of the root test, that series is automatically going to be absolutely convergent. Not every series, though, is absolutely convergent. And it's not a huge deal if it's not. It just gives us the ability to find one extra thing, and it gives us the ability to work with series that aren't like alternating, like we were talking about on Tuesday, which we'll look at as well in a little bit. So the first series I've got right here. So these two series are both alternating series because we've got that -1 in the exponent or in the numerator, and -1 n minus 1, and that one's also. So these are both alternating, both starting off with positive and then going negative and so on and so forth. So let's look at the first example. And all we're going to do to determine if the series is absolutely convergent is basically take the absolute value of it and eliminate any of the negative signs. So if I took the absolute value of the -1 n minus 1 over n squared, I basically just get 1 over n squared. Now, so if I'm looking at that series of 1 over n squared, that by definition is a p series where p equals 2, which is greater than 1, so it's convergent. Which means this series is absolutely convergent. So the negative version of it, the positive version of it, the alternating version of it, any possible combinations of those will always end up working. And that's what the absolute value does. If we look at the next one, this was the alternating harmonic series, which we know from the last class when we looked at it, that this is convergent based on the alternating series test. However, if I took the absolute value of that, I get 1 over n. And 1 over n is again a p series where p equals 1, which is not greater than 1, so it's divergent. So while the alternating harmonic series is convergent, the harmonic series is not, it's divergent. So this one is not absolutely convergent. That's all we get out of it. That just means that the various combinations of them just are not always convergent. We have to look at each individual case in that respect. All right. So notice this isn't really a test that I'm using. This is it's basically allowing me to, it's basically telling me that I can take the absolute value of something, and if that's convergent, then it's every possible combination of its convergent, which means I don't have to deal with the -1 or any negative values in the problem. When we're dealing with the alternating series test, that one has that switch back and forth. So that would be a test that I'd use to be able to do it. But not every series that we're going to have is going to be alternating that would fall into that situation. So if we look at this example with cosine of n over n squared, this one right here is not alternating, but cosine does give me negative values because cosine goes positive and negative. So while it's not alternating, we can't have negative values in it. So I can't use the alternating test or the alternating series test, which we did on Tuesday. I have to do something else to test it. So what we're going to look at is we're going to use basically we're going to look at the absolute value of it to eliminate and not have to deal with the positive and negative ones to see if that could also actually help me prove congruence. So if we look at this problem, so I'm going to take the absolute value of this, the whole thing, over n squared. Now, n squared can never be negative, so I don't have to worry about the absolute value of that. So it's just the absolute value of the top over n squared. So when we're looking at this, we want to look at how this can be convergent. So I know the top is going to always be positive. Since we have that statement, we can look at using the comparison tests. Remember the comparison tests, I had to have it be positive values only, otherwise it won't work. So I know that the absolute value of cosine of n has to be less than or equal to 1. We know that's always true. So I can take this and compare it to 1 over n squared. And I know this value here always has to be less than or equal to that. Does that make sense? So now we're going back to those comparison tests that we did. So remember the comparison test says, so this right here, that's a p-series, where p equals 2, which is greater than 1. So this side is convergent. And since this is always bigger than this, based on the comparison test, this is convergent. So my original series is absolutely convergent. Do you follow the logical flow there or no? Before we go into the actual other tests.
So that kind of just relies on the fact that the adjacent is always going to be less than the hypotenuse or equal to it, right?
Yeah. Because, and remember, the other is also true. So if it was greater than and the other one was divergent, then they both would be divergent. So that was what that comparison test does. Since this one's always less than, it had to be convergent and convergent. Otherwise, we would have had to do the limit test. All right. Now let's actually use it. This is the ratio test. So what the ratio test basically says is if I take a term and the next term for it, that's where you get the n plus 1, that's the next term. So the nth term and the nth plus 1 term. And divide them, which is where the ratio comes in, and find the limit as that goes to infinity. If the limit is less than 1, then the series is absolutely convergent. If that limit is greater than 1, it is, or it goes to infinity, it is divergent. And if it equals 1, this test doesn't help me and I have to do something else.
Why didn't we learn this one first?
Which
It
one do
seems
you
to
mean?
be the most useful one.
Because, actually, this is a great reason why. Because a lot of the little things that we do don't work. So here's an example. Don't worry, I'll go back to the test in a minute. So here's two very simple situations that we've done quite a bit. The first one is just a p-series with n squared. And if you look at the ratio test, the limit comes out to be 1. Here's the harmonic series. The limit comes out to be 1. So a lot of those, like the ones that honestly that we've been doing so far has been p-series and geometric series problems. Even the comparison tests that we did, or even those, all rely back on that p-series or the geometric series. Which a lot of those, when you look at it in terms of the ratio test and the root test that we're going to do in a minute, don't work. So that's why we did those first. These tests are going to be done for very specific types of problems, which we're going to see in a second when we do some of the examples. You're not going to use these tests for everything, because most problems that you're going to use it for, they won't work unless they're in a certain format. So that's why we didn't do it first. So, and that's where that piece down the bottom really comes into play. If it equals 1, we don't know. We're going to have to test something else. All right. Let's look at a problem. So here's the problem. It actually is an alternating series test or alternating series in this situation because we got the -1 in the front. We're not going to use the alternating series test on this. So we're going to use the ratio test for this one. So you can see how it works. So again, since we're doing the absolute value, my -1 piece disappears. So I don't have to actually worry about that -1 piece at all. So an, I'm just going to use as n to the third over 3n. And then an plus 1 is n plus 1 to the third over 3n plus 1. And you're also going to see how hard some of these problems are to actually break down and why we didn't do them first. All right, so now I'm looking for the limit as n goes to infinity of, we don't even need to use the value, n to the third over 3n divided, oh, sorry, it's the other way around. I wrote it backwards. N plus 1 to the third over 3n plus 1 all over n to the third over 3n. All right. Are we good to that point? All right. So it's just a fractional. So we got n plus 1 to the third over 3n plus 1 times 3n over n to the third. So now we've got to simplify this down, do some algebra to cancel some stuff out. So this right here is the same thing as saying 3 times 3 to the n power. Remember when we did that with the geometric series, where we had to get the n minus 1 in there? So we pulled an extra piece out. Same concept here. I can split that 1 off. So it's the 3 to the 3n times 3n. The reason I want to do that is because then I can cancel those two. So this ends up equaling 1/3. And then I have n plus 1 to the third over n to the third. So then we can take that part right there. Since it's both to the third power, I can put it together. And then I can work on the inside. So I got 1 plus 1 over n to the third power. And remember, this is all, I'm doing the limit. So that 1 over n goes to 0. So this is in essence 1/3 times 1. So it's 1/3 is my limit. Any questions or confusions on the algebra steps to go through that? Or the simplification, the breakdown. This is going to be a very common theme when you're going through and doing these. It's going to be very similar in the process pretty much every time. All right. So 1/3, if we look at our ratio test, 1/3 is less than 1. So therefore it's convergent. So that means it's absolutely convergent. All right. That's the ratio test. I'm going to do one more example with the ratio test dealing with factorials, and then we'll do the root test. All right. So this one we've got the n to the nth power over n factorial. All right, so we have an is n to the nth over n factorial. An plus 1 is n plus 1 to the n plus 1 power over n plus 1 factorial. So we're doing the limit of n plus 1, n plus 1, the n plus 1 factorial over n to the n factorial. Does everybody knows what a factorial is?
Yes.
Okay, and we're not sure what a factorial is. It's just so because the next step's going to really make sure you understand that piece.
So that was when it's like 1 times 2 times 3 times 4 times 5.
Yep, exactly. So the key piece here is, and actually why I'm wanting to make sure you actually got that, is because of how I'm going to do the next step. Let me actually just rewrite this as a multiplication so you can see that. All right, so the n plus 1, that piece, I'm going to do the exact same thing I did with the numbers. So this is the same thing as saying that to the nth power. I'm pulling out that 1. I actually can do something very similar with n factorial. So n plus 1 factorial is the same thing as saying n plus 1 times n factorial. Because it'd be no different than saying 5 factorial is the same thing as saying 5 times 4 factorial. Because it's just multiplying 4 factorial by the 5, which is where the 5 factorial would come from. So I can pull that piece out. Because again, when we're trying to take the ratio, we're literally trying to simplify this down and get rid of as much stuff as possible. So now I have n factorial over n to the n, and I can cancel some stuff out. I can cancel the n plus 1s out, and I can cancel the x factorials out. So I'm left with the n plus 1 over n to the nth power. So it's 1 plus 1 over n to the nth power. Now, that limit does not go to 1. This limit right here, so the limit, this is a very special limit. The 1 plus 1 over n to the nth goes to e. So this equals e. That's one of those things that you might want to write down and remember, because that one has a tendency to come up quite a bit. So 1 plus 1 over n to the nth power actually converges to e. Now, in this situation, since we're doing the ratio test, e is greater than 1. So this function is divergent. Any questions with that? Okay. All right. Next one, root test. The root test. Basically the same setup as the ratio test. The only difference is instead of doing the division for the ratio, we're doing the nth root of it. So the absolute value is still in place. The inside, you're taking the absolute value of it. So to make sure that the inside is always going to be positive. But the other stuff is still very true. If the limit's less than 1, it's convergent. If the limit's greater than 1, it's divergent. And if it equals 1, we don't know. I will tell you that there is no point in trying the ratio test or the root test if one of them came out to be 1. It'll still give you 1. So they're basically not really interchangeable. You can't say, oh, well, it equals 1 in the ratio test. Let me try the root test. It's not going to help you. All right. So if either one of them come out to be 1, you have to try a completely different set of tests. All right. So you'll notice these type of problems right here, where you have something raised to the nth power. Oh, sorry. Forgot to switch. When you have something raised to the nth power, that's really a place where the root test becomes really great because it's going to get rid of that nth power and we're just going to deal with the thing that's on the inside. So for this problem, I'm looking for limit as n goes to infinity of the nth root of 2n plus 3 over 3n plus 2 to the nth power. So those two things are going to cancel out. So it's just 2n plus 3 over 3n plus 2. We'll do the same trick that we used in the other problems by dividing the entire problem, the top and the bottom, by n. So we got 2 plus 3 over n and 3 plus 2 over n. So this goes to 2/3, which is less than 1. So it's convergent.
So just real quick, so you just divided everything by n, not by 3n, or do you divide by the largest thing in
The largest
the
exponent. You're divided by the largest exponent, which in this case is just n. So you're not dividing by the coefficient because they want that. So we're not dividing by 3n. If it was n squared, I divided everything by n squared. It's whatever the highest exponent is.
Got it.
Let's look at a couple problems before we go into the other one. All right. So let's look at this one. So the question is which test should we use? Should you use the ratio test or the root test?
The ratio test?
Yeah, we're going to use the ratio test for this one. Basically, the only time you really kind of want to use the root test is when everything's raised to the nth power, because it's going to cancel each other out and make your life really easy.
Is there a way
Well-
to format this one so that a huge chunk of it is raised to the nth power? Like that 10
You
to
could, except that n kind of screws it up. So that n is the piece that kind of messes it all up because it's not raised to any power. So you'd still end up having the nth root of n somewhere in this problem.
which is
We don't know.
like that's just like saying square root of 2 though, right?
Right, but the square root of 2 is different than the cube root of 3. So the nth root of n, we don't know what it goes to, is in essence the problem. So as I said, when you're looking at them, like, let's see, like this is a type of problem like this one here. That one, the root test. Straightforward, simple, definitely do the root test for it. This one. Root test. Because see how they're all, the whole problem's raised to the nth power. So it's like, those are the types of situations where that's going to be helpful to you. This one right here, actually. Because of that ln of n, neither the ratio or the root test is going to help me kind of get rid of that piece. So neither test would be useful for this one. We'd have to do a different type of test for that one. So root. I'll give you another ratio one. So we can see it.
Wait, so for 38, what test would we use again? We would use the comparison?
Actually, 38, we're going to use the integral test.
Okay. Oh, because of that ln?
Yeah, and because of the 1 underneath it, though it's 1 over n. So you'll easily be able to do a u substitution there.
All right.
So these would be ratio. And this one actually is integral. And we're going to see why in a minute. So you can start to see like what process of things are going to work with those. And that's actually what we're going to do next. All right. Here is all the tests. So here's how you decide which test to use. The first two things you're going to look at: P-series and geometric series. So if you have something that's in that format right there, that's a P-series. We use this test. And you're done with it. And remember, you can break things apart in your series. So addition and subtraction, you can break apart. That's going to be helpful to you because if you look at it, you can take and look at the pieces individually. And as long as they all converge, then it's going to converge. So we had, I'm just trying to find the rules here. So we had this rule way back when. That, remember, we can pull out constants and we can split up addition and subtraction. So do that, and that's going to help you break some of these problems down because you might not have to do the whole problem all at once. So we've got that P series. The next one we want to look at is the geometric series. So if it's in either of those formats, that's the geometric series. So those are the first two things we want to look at. And those should be quick to identify. So P series, that P is always going to be a number. So we have 1 over, we got right in the highlighter. One over x squared, 1 over the square root of x. Those are all P series problems. Because the power is going to be an actual number. Your geometric series, 3 1/2 to the nth power. 1/3 times 5 to the nth power. Those are going to be geometric series. Notice the exponent is where the power is. So I can do n plus 1 there. You can do n minus 1. It doesn't make a difference as long as the nth piece is there. The next thing we look for is, can I compare it to a P series or a geometric series? So if I have a problem like the one we did today with the cosine, this one, this is a great example. This wasn't a P series or a geometric series, but I was able to compare it to a P series. So if we can compare it to a P series, I'm good. I'm done. Compare it to the P series, and then I don't have to worry about it. Same thing with geometric. If I can get something to compare to a geometric series, hold on, guys. I'll be right back. All right. So that's the next thing we want to look at is, can we compare them? Any questions with those two tests? All right. Next set of tests. This one is the next piece. That's probably the nice, really cool one to do. Is if you can just literally look at it. Oh, not what I wanted to do. Transparent. If you can literally look at the problem and go, you know what? That limit, if I kept going, is never going to equal 0. Then the test for divergence might be a good thing to use. Notice how we're eliminating a lot of the little things that we have to deal with before we even get to the more complicated tests. So if you look at a limit, and there's a lot of times that you look at a limit and go like, there's the way that it's set up, this problem, the numerator is always bigger than the denominator, things like that, then I know it's going to go to infinity. So I don't have to worry about it. Just do the test for divergence, show that it goes to a number that's not 0, and you're good. Now we start getting into the ones that we have to do a little calculations or a little work for. The alternating series test, if you see those -1s in front, if you see that or that, alternating series test. All right, if you see that there, try the alternating series test on it. Okay. If none of those things work, try the ratio of the root test. The ratio test works really well anytime you have factorials or some product or things that are multiplied together. Okay. So that right there is going to be really good for your ratio test. You'll use the root test, again, when you have something raised to the nth power. And if all else fails, do integration. Notice how that's literally the last option that we're going to look at. These 3 down here, so these 3, change the color of this. I kind of use those 3 interchangeably. We'll look for the 1 through 5 always first. Sometimes, depending on the problem and how it's set up, I might be able to do an integration really easy for it. I might do the integral before I do a root or ratio test. If the integral doesn't look like it's going to be nice, I try something before I do the integration. All right. All these rules right here are in section 1.7, by the way. So if you're missing writing something down or not, these are all in 1.7. All right. Let's look at a couple. How do we want to do this one? What do we want to try? Is it a P series or a geometric series?
It's a P series.
Okay, so what's the P then? Remember, P series. So 1 over x to the P, or sorry, n to the P.
You can't have anything else in the denominator?
Nope. And in this case, I have an n on the top too. So P series has got to be something in that setup right there. And I don't think I can make this that setup. And it's not raised to the n power, so we know it's not a geometric series. So we're not going to be able to do 1, 2, or 3. So the next thing would be the test for divergence. Remember when you're looking at your limit. So there's a couple things. So remember, the test for divergence is basically looking at a limit. Does it go to 0? And if it doesn't go to 0, it's divergence. We're done. If it goes to 0, I got to try something else. Anytime we're dealing with a fraction, especially one like this one where it's really easy to look at and there's nothing really crazy there, if the numerator, so if the degree of the numerator is greater than the degree of the denominator, the limit goes to infinity. So if the numerator is bigger than the denominator in terms of degree, it goes to infinity. If it's the opposite, so in this case it's greater, if it's less than, it goes to 0. If it's equal, it goes to some number. Not 0, just some number. All right. So now how does that help me in this situation? What's the degree of the numerator?
1,
What's the degree of the denominator?
1.
1.
So
Therefore,
they're
it's
equal.
not going to 0. So I know this is going to go to something that's not equal to 0. So it's going to diverge. So let's do the quick test for divergence so you can see what it goes to. So we can show that if we divide everything by n, I get 1 minus 1 over n and 2 plus 1 over n, which goes to 1/2. So it is divergent by the test of divergence. So that's the thing. When you're looking at a problem, if that's the case, it's like it's pretty quick to see that the test for divergence works or is useful. Worst case, you try the test for divergence and you get 0. And then you go about your business doing the other problems. So worst case, you try something that doesn't help.
So Professor, just make sure I understand this here. So what we're saying here, obviously we're looking at a series, not a sequence. So we're saying that all of these numbers are going to add up to 1/2 eventually.
No,
We're saying that that they're headed towards the value 1/2.
we're saying the sequence goes to 1/2. The
Got
sequence, not the series. Now, that's actually really important because if the sequence doesn't go to 0, every number that I'm going to add, the last number I'm going to add is still going to make the number bigger than it was previous. That's why it's divergent.
Right.
So if it goes to 0, I don't know. It could diverge. It might not. It might not diverge because we've seen situations where that. But I know that the next number I'm going to add isn't going to make it any bigger because I'm adding 0.
So if the sequence does go to 0,
Then we have to do some other test. We don't know.
We don't know. But if it
Because-
if it is greater than 0, we know that it is divergent.
Correct. Yep. If it is not equal to 0, I know it's divergent. Because if you think about it, remember, we have the harmonic series, which is just 1 over n, which does go to 0. When I do the limit of that sequence, it does go to 0. But that one's divergent.
Right, we still need to run more tests. Okay.
Right. Where 1 over n squared is a p-series, but when I do the limit, it goes to 0, and that I know is is convergent. So that's where that 0 one doesn't tell me anything. And that the test for divergence says, as long as it does not equal 0, I know it diverges. If it equals 0, I got to try something else. But it's just one of those quick things to look at before you try something else. Because again, it's simple and it's quick. Like this situation. The next problem we'll look at. So if I look at this problem right here, what's the degree? What's the degree of the top? We know it's not, well, first off, we know it's not a p-series and we know it's not a geometric series. So it's not going to be those two things. We might be able to do a comparison, but if we look at this quick, the degree of the top is 3/2, the degree of the bottom is 3. So I know right there that this limit goes to 0 because the degree of the bottom is higher than the degree of the top. So test for divergence isn't going to help me. That's what I'm talking about when you're looking at things logically. Look for things that are quick. Look for things that it's like, okay, I know it's not going to be that. Let me try something else. This one, actually, the easiest way to do it is we actually can do something just similar to what I was just doing. I know the top is, the biggest one is 3 over n, or n to the 3/2. The bottom is 3n to the 3rd. Which if I clean this up a little bit, I have 1 over 3n to the 3/2. I can do a comparison test. Because I know that that piece of information is going to help me. Does everybody see how I broke that down to the p-series? The question in this one, though, is based on what I've got right here. I don't know if I don't know which direction this is going to go. I know this converges because it's a p-series and p is 3/2, which is greater than 1. But I don't know if it's greater than that or if this is less than it or greater than it. So I would have to do a limit comparison test to be able to show that. Okay. All right, what about this one? What would you want to try on this one?
Wait, so on the comparison test, all we had to do was recognize that 3 over 2.
For what I'm doing right now, yes, you just have to identify it.
No, the one before that, yeah.
Yeah, this one, all I'm really doing right now is I want you to understand which ones you're using. Like which test, looking at it, which test am I going to use? Because some of these are really complicated calculations out like this one.
So what I'm trying to say is I thought we left off, is it greater than, is it less than? But we didn't have to do any of that just because the P is greater than 1 and we know it's converges, right?
Okay, so this problem right here, we don't know if it converges or diverges yet. I didn't find the answer to it. We do know that we have to do the limit comparison test to find the answer to it. All right, I'll do it the limit comparison test. I'm just not sure how this is going to work out because that's a complicated problem. So let's see what happens. Let's see what happens. Oh, it was an over b. So we got n to the third plus 1 over all over. Okay. So we've got square root of n to the third plus 1 over 3 to the third plus 4n squared plus 2 times 3n to the 3 halves over 1. And yeah, that's why we didn't do this problem out. So we've got 3n to the 3 halves, n to the third plus 1 over 3n to the third plus 4n squared plus 2. So I've got 3 n to the third, n to the third plus 1, n squared plus 2. All right, I'm going to divide everything by n to the third. So I have 3 pulled inside, that is 1 plus 1 over n to the third over 3 plus 4 over n plus 2 over n to the third. The limit of that goes to 3 over 3, which is 1. And the limit comparison test says as long as it equals some number that is greater than 0, so that's greater than 0, this converges because the other one converged.
Wait, so the limit test comparison test is as long as it equals a number greater than 0, right?
So it can't be infinity, it just has to be a number greater than 0. So it can be 5, 10, 20, 50, whatever you want it to be, as long as it is not 0 and not and it's a real number, then it works. In this case, it comes out to be 1.
So that wasn't necessarily hard, it was just arithmetic, yeah?
Yeah, it's just a lot of little pieces to break down. So it's not hard, it's just a pain in the butt. Lots of little places that you can make mistakes in. The nice thing about most of these is most of them aren't hard. It's just a lot of algebra to break things down sometimes. All right, let's look at this one.
Just kind of, sorry to do that to you, but on the previous one, n to the third over 2 divided by n over 3, that's not 1 over n over 3, is it?
Hmm?
So on the second to last part there, I
Yep.
see why that n to the 6th, to the half power, that's n over 3. So divided by n over 3, that's 1. but then the next term over, n to the third divided by 2, so n to the 3 over 2 divided by n over 3.
So
That
right
would be-
here, okay.
Just making
Uh,
sure I'm not missing anything.
Nope. So this right here ends up becoming n to the sixth plus n to the third over n to the sixth. When you bring in the 3, it's basically n to the sixth. So it's that whole thing. That's how I got the 1 plus 1 over n to the third.
N over 6. Oh, okay. So you put it in there, right? By
Yeah, it has to go
doubling.
inside the square root.
Okay. So that still gives us 1 over n to the 3. I see what you're saying. Got it. Okay.
Okay.
Yeah, because I was thinking, wouldn't like isn't it technically n, or if you were looking at it the way that I guess I was, it would just n to the 3 over 2, right?
No, you can't do it that way. Because you can't take the square root for each piece.
Oh, is that a violation? Okay.
Yes. That would make our lives a lot easier if we could, but you can't do that.
Got it.
Because then at that point, it's mostly the same thing as saying like this. Here, I'll just do one real quick. This is why it doesn't work. If we add the square root of 25 plus 49,
Mm-hmm.
that's the square root of 72,
Mm-hmm.
which does not equal 5 plus 7.
Oh, tricky. Thank you. Okay.
Well, all right, next one. Which test do we want to try for this one? So go through the quick, easy ones. It's not a p-series. It's not a geometric series at all. There's no way to make them either one of those. So we can't do the limit comparison test or any of those tests. If we look at this one, the limit as n goes to infinity, I could actually probably make the argument that it's going to be zero, or not zero, I mean, because this is going to go to basically 1. Oh, actually, no. Yeah, that's going to basically go to 1. And it left with n. However, the other thing you can use on this one is the integral test, which actually works really well for this one. Because yeah.
What was the first part again, Professor? Sorry, I didn't catch that.
So
You said, yeah.
you could, so like if I did the limit as n goes to infinity for this, which is just the test for divergence. As n gets increasingly large, so I'm going to rewrite this a little bit. And e to the, oh wait, yeah, that's right. So this right here, that's why this becomes 1 over e to the n squared. So, oh, that's going to 0. That's right. That's going to 0. Never mind. So this is going to go to 0. So the test for divergence does not work. That goes to 0. I was thinking that goes to 0. This piece up here went to 0, and that doesn't work. This is why doing things quick in your head sometimes works, and then when you try it, it doesn't work. Yeah, I was looking at that and going, oh, that's a fraction. That's 1 over something. So that's going to go to 0, which means e to the 0 is 1, which would have been nice, but it doesn't actually work. That's what I was trying to do quickly in my head. So the test for divergence fails. Failed.
And just for the sake of repeating what that test for divergence means, the test for divergence means as long as if it is greater than 0, that means it is going to infinity, but because it is not greater than 0,
If
inconclusive.
it doesn't equal 0,
Right.
that's it. Doesn't equal 0. Doesn't have to be greater than 0. Just doesn't have to equal 0, which means it could be negative.
Oh, got it.
It just cannot equal 0. So it failed the test for divergence. So we've got to try something else. You can actually do either one. You can actually do the ratio test for this one or the integral test. This one works really well for the integral test because of how it's set up with that n in front. So I can do the integral test pretty quickly for this one. And it's a good one to actually show you the integral test just to renew your understanding of it. So I'm going to have x e to the negative x squared. So I'm going to make u negative x squared. So du equals negative 2x dx. So I've got negative 1/2 du equals x dx. So I can pull out the negative 1/2. So 1 to infinity. And this becomes just e to the u. So I'm left with negative 1/2 e to the negative x squared. Evaluated from 1 to infinity. All right. So if we look at this one, we have the negative 1/2. If I plug in the infinity, this is going to go, well, this whole thing right here is going to go to 0 because of what I just did up here. So that goes to 0. Minus, if I plug in the 1, I get e to the negative first power, which is 1 over e. So I end up getting negative or positive or equals 1 over 2e. So since this actually does go to a specific value, it is convergent. So this is convergent.
So the integral test says that as long as it goes to a
The integral-
specific,
Yeah, as long as the integral is convergent, the series is convergent, which means the integral goes to a specific value.
which again, it doesn't mean that the whole series adds up to that. It just means that the last number in the series is going to be.
Well, and this one actually doesn't even really tell you that. This just tells you that it's, so the integral test, remember, is adding up all those extra values. It's showing you the area underneath that curve. So it's getting closer to the sum because we're not looking at the series in this case. We're not looking at the sequence. We are actually looking at the series, but we have a bunch of extra stuff added in that's above those boxes. So all this one tells me is that it is convergent. It doesn't, that 1 over 2e means nothing in terms of the actual problem.
Well, what I'm trying to say is this. So this specifically, when we say the series is convergent, we're not saying that they're all adding up to 1 over 2e, 1 over 2e.
No.
We're just saying the last item in this theoretical sequence is 1 over 2e, right?
No, we're not even saying that.
What are we even saying?
So that 1/2e has no connection to the actual problem in this situation. So remember when we're doing the limit, when we're doing the integral test, here, I'll show you, remember what the integral test is. So let me get a picture of it.
No, I know. I guess I'm just saying, or not. Sorry, you're right. I understand why the 1/2e, because we're dealing with the integral, not the sequence itself. I get that part.
Yeah.
What I'm saying, whenever we say a series is convergent, we're saying, what specifically are we saying in terms of?
We're
using the-
saying it goes to a specific number.
But when you say it goes, that's very ambiguous. Are we saying this the last item in the
series.
sequence?
No. When we're talking about the last item in the series or the sequence in this one, it's 0. The last item in the sequence for this one is 0. That's what this limit, that's why the test for divergence failed.
Okay.
We're saying this series is convergent to some number. This series, when I add up all the values all the way out to infinity, is going to come up with a specific number.
And we're not saying what that number is.
Right. I do not know what that number is. I just know it is some number.
Yeah. Okay. Okay. Wow.
That's what convergent means. It's going to a number. We don't know what the number is. We can calculate that number. We have computers and stuff that can come up with that number now real easily. And I showed that when we did the actual integral test, I showed you actually how to do it. And then I showed you how to do it in Desmos to come up with the exact number that it converges basically to. So we have that ability now. But what we're trying to do here is we're trying to figure out, does it converge or does it diverge? If it converges, then we can do other stuff if we need to. If it diverges, we're done.
Cool.
Okay.
Thank you.
No problem. All right, next one.
In that last example, Professor,
Yeah.
with the integral test, you have to have that continuous positive and decreasing, right?
Correct. Yes. And I didn't actually test that. I just assumed it at this point. But yes, you do have to make sure that it's continuous, that it is positive, and that it is decreasing. The
Thank you.
limit test right here kind of gave me the fact that it was decreasing because it's going to 0. So that kind of took care of that problem. I knew it was positive because E is never going to give me a negative number and the N is never going to be negative. And there's no value that would work. So I knew it was continuous. I just didn't actually go through and show those out. So, but yes, so depending if the problem is not easily identifiable as positive, decreasing, and continuous, you do have to show those things. This one was quite obvious. All right, next one. Which test do we want to use for this one?
So just talking out loud here, the denominator being larger, right? Obviously, there's an alternating factor, and then the denominator being larger means that it's going to 0, right?
Yep.
Oh, sorry. I should got to stop just saying that. That the last value in this sequence is going to
The
be 0.
easiest way to say that is the limit as n goes to infinity is 0. That's how you say that.
When I think of limits, I just think of what it's getting closer and closer to, which I guess, yeah, is the last sequence, right?
Right.
Sorry. Cheers.
So the limit of this, remember, we're just looking at that part right there, does equal 0. And we could show that just by dividing everything by n to the 4th if we wanted to. We don't have to. But it does equal 0.
Which means it's not divergent, but that's all we know.
Right, it fails the divergence test. But remember, for the alternating series test, we have 2 pieces of information that we need. We need to know that the limit is equal to 0, which in this case it is. And we need to show that it's decreasing. So we need to show that n to the third, n4 plus 1 is greater than, or, well, yeah, I'll write the thing where they're doing it. I gotta move my numbers over now. All right, n to the third over n to the fourth plus 1 is less than n plus 1 to the third over n plus 1 to the fourth plus 1. That's true. All right, so we basically have to show that this is decreasing. When the numerator and denominators change, it's a little more complicated than just when the one of them changes. Like if just the numerator changes, it's probably not going to be decreasing. It's probably increasing. If just the denominator changes, it's probably decreasing. When they both change, it becomes a little more complicated. Yes, in this one, it's probably pretty obvious because the bottom's getting bigger faster. But the easiest way to show that for sure is just to do the derivative. So the derivative of this one, remember, it's the derivative of the top. So it's 3n squared times the bottom minus the derivative of the bottom, which is 4n to the third times the top over the bottom squared. And then we just, bottom doesn't matter because the bottom can never be negative. So we're just looking at the top. So I have 3n to the sixth plus 3n squared minus 4n to the sixth has to be less than 0. So I got negative n to the sixth plus 3n squared is less than 0. So I can pull out an n squared. And I have 3 minus n to the fourth is less than 0. So the n squared is just would be 0, so I don't have to worry about that one. So I have 3 minus n to the fourth is less than 0. So I get n to the fourth is greater than 3. So it's the n is greater than the fourth root of 3. So as long as that's true, it's decreasing. And that's basically just over 1. So we're good. It meets that criteria. It met that criteria. So it is converted.
Professor, I'm a little lost after the bottom left calculations there. So you simplified everything out, 3n6 to the 6
Yep.
plus, right? And what are we saying when we say that's less than 0 again?
Because remember, I want my slope. The derivative is telling me my slope.
Right.
So if my derivative is less than 0, my slope is negative, which means it's decreasing.
Right.
That was my goal. Remember, I'm trying to show that this function right here, or this series, decreases.
Okay. So then we're
So-
trying to show that.
Right, so as long as my slope is negative, it's decreasing. So this has to be less than 0.
Right.
So-
Okay.
Factor it out. N squared is less than 0 would mean n is 0. Because that has to, there's nothing else there.
Mm-hmm.
So then I take the 3 minus n to the fourth is less than 0. And solve that. And n has to be greater than 4, the fourth root of 3 to make that true. As long as n's greater than that, my derivative is negative, which means my function is decreasing. Which means criteria 1 is true.
Got it. Thank you.
No problem.
And then for the second one,
That was
well, we
did
know
here.
that we already did that there. So then we're saying it because it passed both tests. It's converted.
Correct. Yep. And the reason why I always do test 2 first is if it didn't equal 0, it's divergent because of the test for divergence. So I don't even have to worry about the next step. That's why. I
Right,
was
so
just-
whenever something fails the divergent test, it already passes that second one, huh?
Yes. Because it equals 0. That's the nice thing about doing that one first. Because in essence, you're testing the test for divergence and you're meeting one of the criteria of the alternating series test. Two birds, one stone. All right, let's look at this one. What do you think we're going to do with this one? This one's got a factorial in it. So what rule did we say we're going to do with factorials? That was the ratio test. So if we look back here, basically anything that involves factorials and other products, use the ratio test. And nothing before that point. I totally switched the wrong screen. Nothing before this point in the process has anything with factorials on it. So whenever you see factorials, the ratio test is probably going to be your easiest one to deal with. So we've got AN is 2, oh, 2K, A and K there. K factorial, A K plus 1 is 2K plus 1 over K plus 1 factorial. So we're doing the ratio. So we've got 2K plus 1 over K plus 1 factorial. And I'm going to flip this up so I don't have to rewrite this twice. Over 2K. So remember the top piece up here, that's just 2K times 2. And this one down here is K plus 1 times K factorial. So the 2K cancels out the 2K, the K factorial cancels out the K factorial. And I'm left with the limit as n goes to infinity of 2 over K plus 1. And that goes to 0. So remember the ratio test? We did that one a few minutes ago or a little bit ago. What is it? When it goes to 0, what does that mean?
Inconclusive?
No.
No.
It's when it goes to 1, it's inconclusive.
Oh,
This is less than 1, so it converges. All right, one more to go. All right, so last one. What do you want to try for this one? So we've got 3 to the n right here, right? So that kind of looks like a geometric. So let's compare it to 1 over 3n, which remember is 1/3 to the nth, which is 1/3 times 1/3 to the n minus 1. So that's my r. And since r is less than 1, that converges, correct? So that's what we're going to compare it to. So the only question that we have is this true? Is this less than that? And we don't have to do much work because the only thing that changes is in the denominator. I'm adding 2 to it. That means my denominator is getting bigger, so it is less than that. So since that's true, this function converges. All right. Any questions on that one? Okay. Then we are done. My suggestion, if you want to practice these, I personally would not practice sections 11.1 through 11.6. I would practice section 11.7. So section 11.7 has, and I'll even put them in here. There's 38 problems. The key piece of information is it doesn't tell you which test to use. So you have to figure out the test and then test it for convergence. All right. Honestly, that's going to help you more than just testing all the tests. All right. This is going to help you a ton, much better on the test than doing the other ways. Because you get to do all the tests basically. All right.
So just start with 11.7 straight up.
I would literally do these 38 questions in 11.7. Or maybe not do them all. There's a couple, like I haven't done any of the hyperbolic trig functions and stuff, but the majority of these you can easily do. So it's like, look at the tests, figure out which test works, and then go through and do the test, then do out the test.
And this is one where the odds are in the answers book, are in
Yep.
the back
The
corner.
odds are in the answer book, and if you send me an email, I'll send you the answers for all of them.
Thanks, Professor.
So, all right, any questions? All right. If not, then I will see you next week.